There are two additional video recordings related to clays and clay-water interaction. The purpose of this summary video is to bring all these pieces together while at the same time benefiting from images that can be shared through PowerPoint. So once again, the key here is to see not only the clay, but how do clay particles, small grains, interact with water. Let me start by sharing with you some images obtained with a scanning electron microscopy of some of the characteristic clays. On the top left, you see the kaolinites forming booklets, and you can see some of the corners that tend to form a little bit of hexagonal shapes, not so clearly seen in this image, but you will see them quite frequently in kaolins. On the right-hand side, you see the illites, at the bottom, smectites, and then to the right, halosites. And as you can see, they are not platy, they are tubular, and these ones in particular have formed from the weathering of volcanic ash. So you come back 10,000 years later after a volcanic eruption, and this is what you find. So that means that there has been significant weathering in relatively short geological times that have evolved a material that is amorphous glass to these type of clay minerals. Now, one important characteristic is that they have very high specific surface. Specific surface is in the denominator of an estimation of pore size, which is the void ratio over the specific surface, but it is also critically important for permeability, as we will see when we get to the Kosenik-Karman equation, where specific surface goes in the denominator to the square. So let's do some computations. For example, if the porosity was 0.2, and sorry, but you have to convert from porosity to void ratio, then you use the equation above, and for a kaolinite with 10 meters squared per gram, the mean pore size would be 10 nanometers. However, for illite, it would be 2 nanometers mean pore size, and for a montmorillonite and smectite, it would be 0.3 nanometers. We are really at the atomic scale. Clearly, this is for a small porosity of 0.2, which is what happens when the clays become loaded by their self-weight as they become buried in the subsurface, and probably they become shales. Now, there are many small size particles which are in the clay size range, but they are not phyllosilicates. For example, there you have on the left-hand side the diatoms with a zoom in on the lower left corner for Aminifera coccolith, but you also have the chemical genesis, and you have the hematites, the beautiful crystals from galena, pyrite, and sphalerite. Now, going back to the clay minerals, we have to build the structure like if we were building a house with Lego blocks. We have to start at the level of the building blocks, the silica tetrahedron and the aluminum or magnesium octahedron, with oxygens on the vertices in the silica case and with hydroxyls on the vertices in the case of the octahedral structures. And then we put them together forming sheets, and these sheets together, they bond through shared oxygens, and they form the layers. And whether it is a 2-to-1 layer or a 1-to-1 layer, they define different clay structures. When you see the silica tetrahedron from the top, you see the typical hexagonal structure that gives rise to the shape of primarily kaolinite particles. By the time we have these layers interacting with water, they become separated, forming the counter-ion cloud. And in this case, you have a 2-to-1 layer separated by water with respect to another 2-to-1 layer. And this is the result of molecular dynamic simulations. And now we are at the nanometer scale. probably across here, we will have 15, 20 angstroms. So we have 2-3 nanometers across. Now, when we have many of these particles together, we thought about these edge-to-face and edge-to-edge aggregations, but actually, by the time they get buried, they tend to bunch together and they form these tactoids. Now we are at the micron scale. And when we zoom out even further, we see the layered shale structure. So please notice that we have gone from an angstrom scale to the millimeter scale of shales, and actually we see shale formations that run for hundreds of kilometers. So we are jumping a huge number of orders of magnitude in a scale in our trying to understand the behavior of clay sediments and shales. So let's go back to the basic building blocks, the tetrahedral element with the silica at the center and the oxygens in the vertices, and the octahedral elements with aluminum typically, but it could also be magnesium at the center and hydroxiles on vertices. We represent them with this type of shapes in order to make the sandwiches. And remember that they're going to be bonded together by sharing oxygens. Typically, we're going to see the gibbsite, except in one of the cases that I will show you next. So these are the most common families of these sandwiches. The one-to-one, the gibbsite bonded with silica, forming kaolinite. And you see that the thickness is approximately 7.2 angstroms. Now, by the time we go to the 2-to-1 sandwiches, the thickness is going to be in the nanometer scale. For example, for montmorillonite, is 9.6 angstroms from here to here. And that will determine where the peaks appear in XRD, X-ray diffraction signatures. Now, the 2-to-1s can be bonded with potassium in between, or there could be a brucite layer in between for the case of chlorides. So if you have montmorillonite and there is lots of potassium, a process called illitization takes place, where potassium replaces other ions, bringing particles, layers together to form these thicker particles that we call illite, and hindering the swelling between these particles by the incoming water. And so these are going to be non-swelling clays. In fact, there is still double layer interaction between these sandwich materials. And so there is still some swelling capability, but nothing compared to the smectite. Now, there are other materials that have similar chemical composition. However, they are amorphous because they will not give us a clear signature on an XRD, and these are typically called alophanes. And because they don't form continuous sheets and they are smaller and they are more broken, they can give us a larger specific surface. For smectite, the theoretical specific surface is something like 720 meters squared per gram. However, for alophanes, it can go even higher, reaching 900 meters squared per gram. Huge specific surface. Now, let's take a look using molecular dynamics at a dry clay and a wet clay. In a dry clay, because there is charge, there must be counterions. And so where do those counterions sit when the clay is dry? Well, they sit there within the holes in this hexagonal shape formed by the silica tetrahedra bonding together, sharing oxygens. And that is where the counterions, the blue, in this case sodium, are sitting in those holes in the layer. Now, if we see the wet clay, first of all, recognize the following. This is the octahedral layer made of aluminum. This is the gibbsite layer, but there has been an isomorphic substitution. Notice that here we have put the magnesium instead of the aluminum, and then at random, there is also substitution in the tetrahedral layer, the silica octahedral layer, and there is an aluminum replacing the silicon. And so this clay has become charged. The counter ions are the blue ones, in this case sodium, and they are already hydrated by water molecules, and they have been pushed out of the surface. Here they are attached to the surface. Now the water molecules went in and knocked them off, hydrated, and now they are in the counter ion cloud. Now, when we look at a single particle and we let it wet, where do those counter ions sit? Well, they are hydrated, but a hydrated counter ion is still a charged quantity. Let's say the sodium with all the hydrating water molecules. The water molecules are electrically neutral, but the sodium remains with its positive charge. So there is still an overall attraction, but there is thermal activity that kicks it out, and that leads to the development of this counter ion cloud or double layer. Now, eventually this decreases exponentially, and so they tend to be closer to the surface than further away. And that is the essence of double layer theory. First of all, we need to understand what potential is. Potential is the work that we have to do to bring a charge from infinite to a given point. Now, if I'm working against the field, let's say that this is negative and I have a negative charge, so I'm pushing it against, and the closer I come, the higher the repulsion, the higher the work I have to do. So if I integrate all the work from infinite to a given location, that is the potential, the amount of work that I have done to bring that charge to that location. You can find it in our book. In fact, this will be in the appendix of the book. This is called the Poisson's equation. The change in potential between two locations, so the second derivative of the change, the second change in the potential with respect to x, is equal to the excess charge at that location. So if there were no charges, there would be no change in potential. But if there are charges, that second change in potential is the excess charge. Now I can relate excess charge, which is what we do from an electrical point of view, but from a chemical point of view, we're going to use the concentration. So now charge is concentration times valence, but I have to multiply by a constant that will relate charge in coulombs to concentration in moles, and that is Faraday's constant. So now I can relate concentration, a quantity that we rarely measure, to local charge by this relationship. And you see the summation is because I have both counter ions, but I also have the anions and the cations, as you will see in this figure. So the anions don't want to come close to the surface. The counter ions, let's say the cations, want to be close to the surface, and the excess charge will be the difference between these two. Therefore, that is the summation. Now, from Boltzmann equation, I also have a relationship between the concentration and the potential at any given distance. Bring these two equations together with Poisson's equation, and I play a little bit with the mathematics, and I get that the potential will decrease further away from the clay surface following an exponential relationship. And this is the red line that you see here. That is this solution. Now, whenever you have an exponential decay, there is no characteristic length scale. Like, for example, if you have the sinusoid, the distance between two peaks is the wavelength or the period. There is no characteristic length in an exponential decay. And so we always take the distance where the potential at the origin decreases by 1 over E. This is the Euler's number, as the characteristic length of an exponential decay. And so if we do that, this is now what we are going to call the thickness of the double layer, or the characteristic length of this exponential decay, sometimes also called the Debye-Huckel length. And so now the equation of the potential is the potential at the origin decreasing exponentially with distance related to a characteristic length beta. And this beta, by the time you plug it into all these equations, becomes this, which relates to this, which is the heuristic that we used in a previous video. So this thickness of the double layer, once again, realize that this is not a fixed number. It's the ratio of the potential decrease with respect to the origin by 1 over E. This thickness of the double layer is proportional to the permittivity of the pore fluid. Let's say 79, 80 if this was water, or 5, 6 if this was an organic fluid. The temperature, which will be in kelvins, by the time you plug into all these equations in order for them to make sense, the concentration in moles per liter, and the valence. Valence square. This denominator is called the ionic strength. Now, valence can be 1, 2, or 3. It changes, but not so much. This can vary in orders of magnitude. So this is really the one that we have to pay more attention, but of course, valence plays a very critical role as well. And based on this relationship, the other ones being constants, based on this relationship of proportionality, we were able to make many important observations related to heuristic observations, related to the impact of changing fluids in the behavior of clays. Now, there were several constants here, Paradise constants, the gas constant R, where is K, this K, which is Boltzmann constant, and then the other one is the charge of an electron and Avogadro's number. Now, there is a relationship between all these universal constants, which is here, and this is the one that we use to go from this function of the thickness of the double layer to this expression, which is the one that is more useful for computations. Now, there is a problem with the previous equation by Wee and Chapman, and that was that it assumed that the charges were point size, in other words, infinitely small. However, when we begin looking closer and closer to the surface, we cannot disregard the fact that charges have their own size. And so as we approach the surface, this exponential decay doesn't work anymore, and there are quantum jumps on the potential. Why is that? Because some of the counterions were hydrated, but were not kicked out completely out of the surface. There was one water molecule in between them. This is a water molecule, and this is called an outer sphere complex. And even more, some counterions were hydrated on one side, but were still bonded to the surface on the other side, forming an inner sphere complex. Therefore, as we are approaching here, and we are, let's say, in the last 6, 10 angstroms away from the clay surface, we have to acknowledge the atomic size of charges and hydrated charges. And so what we think of the thickness of the double layer and the exponential decay is further away from this layer where the diffuse layer is. This layer where the jumps are taking place with inner and outer sphere complexes is called the Stern layer. And in fact, we seldom get to feel the surface potential because what we are actually feeling is the potential at the Stern layer. And we have to be far away for the bulk electrolyte, which, by the way, the ionic concentration here is pretty much controlled by the excess salts in a dry clay. This is what we're going to wash away, whatever salts are in the bulk fluid, when we wash a clay with deionized water. Once again, we can identify now the thickness of the double layer, but we are going to do it typically in relationship to the potential at the Stern layer. And this shorter area, which is the Stern layers, the separation is also called the outer Helmholtz plane. So let me go back. And this was what we had originally assumed. Now we have to make the modifications to acknowledge the point size of charges. By the way, sometimes we don't even measure the surface potential. We don't measure the Stern potential. One of the ways to measure surface charge is to put an electrical gradient, a field gradient, and let the particles migrate. And and we see the migration velocity, and we can change the pH and we'll migrate in the other direction in this electrophoresis test. And part of the counter-ion cloud is moving with the particle, but part of it gets shear, and new charges come and to join the particle as the particle is moving. And so what we see is the potential at the distance of that shear plane, and that is called the Zeta potential, which is different from the Stern potential and different from the surface potential. So when we read the literature, we have to be very careful and to distinguish how were measurements made and what is the actual potential that can be inferred from those measurements. We also said in previous presentations that clays are charged for different reasons. One, because of isomorphic substitution, and the other one, which that was the inherent part, and the other part was related to pH and the pore fluid. And here is a bulk measurement of surface charge with respect to pH. The lower the pH, the more positive the surface charge tends to become. But the surface charge is also dependent on not only on the pH, but on the balance of the prevailing ions and the concentration of ions. So it's a fairly complex story that will affect some of our analysis as we move on. Above all, let's recognize that surface charge can be altered by pH because of protonation and deprotonation, particularly in the gibbsite layer, in the octahedral gibbsite layer. So if we do the analysis based on these bulk measurements and electrophoresis, we recognize in the past that particles will tend to aggregate differently depending on these two parameters, the electrolyte concentration and the pH. pH determines the surface charges, while the electrolyte concentration was telling us whether we collapse the double layer because the concentration is too high. Go back to the heuristic equation, concentration high, double layer thickness small, and so van der Waals takes over, and then particles become aggregated. We concluded on this fabric map based on lots of measurements were done based on sedimentation, viscosity. We cannot really do much based on SEM because by the time we dry the specimen, we alter its fabric. So sometimes there was cryogenic approaches, but there was really quite a lot inferred from bulk measurements. And the story gets complex, for example, in kaolin, because one side may have a different charge than the other side. So let's look deeper, and then with atomic force microscope, we can go and check the potential on one side and the other side. And in fact, we can go and see the potential on the edges as a function of pH. And so recent data show us that. And we see that the gibbsite surface changes its surface charge by the time the pH is about 6.5, the edges around 5, while the silica phase, the silica tetrahedron phase of the kaolin hardly changes it does change the surface charge, but it remains negative even to very low pHs. Now, this is important because now we could have one phase being positive while the edge is negative. That means that these ones will attract, or one phase being positive while the other phase is negative. That means that the two may attract from different particles, and that will determine now a more clear fabric map for kaolins based on these critical changes as a function of pH. So here we go. This is the 6.5, this is the 5. And if you go back to the previous one, you can stop this recording and go back and forth, and you will be able to recognize the cause for these different fabrics. If all the charges are negative or all the charges will become positive, you tend to have a dispersed fabric. And by the time we have a high ionic concentration, now we just collapse the double layer and it tends to be aggregated. but there is an effect of pH with ionic concentration in controlling charge, as you may have seen in the 2 or 3 earlier slides. And so this is the reason for the curvature of this front. Please analyze this map in careful detail based on the previous slides. Now, that was clear for the kaolin, and kaolin is a one-to-one clay, so it's a gibbsite and a silica tetrahedral phase. And so they change with pHs are different, but what happens if we have a 2-to-1 clay where we have silica tetrahedra phase on both sides, which has a lower sensitivity to pH? What would be the fabric map in that case? It would be strongly controlled by the pH sensitivity of the edge. But furthermore, let's look at things in real scale. This is the thickness of a kaolin particle, let's say 100 nanometers, and the thickness of the double layer is 10 nanometers. So this is the way the thickness of the double layer would look around a kaolin particle. But what happens in a fully swollen montmorillonite? Well, the particle would be 9.6 angstroms, 1 nanometer, but the thickness of the double layer, if it is still 10 nanometers, would be much, much thicker than the particle. By the way, the relative size here is correct, but I had to change the scale from the previous drawing to this drawing, otherwise we cannot see it. We cannot see the double layer in the uppercase. Now, if the thickness of the double layer is so thick with respect to the particle, you realize the critical importance of double layer phenomena in montmorillonite, the fact that the phase may almost hide the edges, the electric field that forms around, and conversely, the relatively low effect of double layer thickness on kaolins. This will play a critical role in our understanding of clays, which are at the extreme of clays, the montmorillonites, and the clays that are in those transition conditions where electrical interactions begin to gain relevance, particularly at low effective stress. Now, as clays become buried deeper and deeper, and recognize that it's just not pure clays, there will be silicates and there will be carbonate particles and other precipitates. Now they begin getting stiffer and stiffer, and it gets to a point that we don't know if it is a clay anymore, if it has become a rock or a soft rock, and then that transition. And in fact, when we take SEM images, we see that there are all these rotund particles, which are precipitate particles, and the pyrites and the organic matter, all this with pores, all this is organic matter that got buried with the clays. And so this is a shale. But when we look at this, you see many more things, like, for example, these packages of clays, laminates that are coming together, splitting like if you were splitting cards, playing cards, and separating and probably breaking with lots of bending. These must be very flexible structures. And so by the time we're at this point, these tactoids, these bunches, do inherit properties from the atomic scale processes that we have just described, but collectively now they are behaving in the micrometer scale, very mechanical. And this is what this drawing is trying to show you. If you go back and you analyze all the forces that control behavior, remember the weight and the capillarity, this is the range for sandcastles. And we also look at the forces, DLVO forces. When do they begin causing strains? For example, if you just change a pore fluid, which is pure water, to seawater, we have no strains in the silts and sands. We begin experiencing strains in the clay-sized minerals or particles. And so what this is telling us is that when we go back to this multi-scale analysis, all this was electrical, but by the time we get to the tactoids themselves have properties that come from electrical interactions, but their interaction between tactoids, among tactoids, now becomes very mechanical type. And that is the way we do upscaling in all this system that goes from the angstrom scale to the hundreds of meters scale or kilometers. And we have attempted that. And so we simulate particles, and the particles are like beams with the stiffness that are obtained from the atomic scale and forming tactoids. And you see how they bend around precipitates, which could be carbonate, silicates, or pyrite. And the black ones is organic matter. Remember that organic matter that got buried? And this was originally quite spherical, but the organic matter is quite deformable. So not only the clay particles that form the organic matter deforms. What is surprising is that these part at the beginning, when we put them in the suspension, they were randomly oriented, like the red histogram shows. This is a polar histogram. But by the time they begin getting buried under zero lateral strain boundary conditions, the particles from random organization begin getting flatter and flatter, as you will see, in this case, probably simulating something like 1 megapascal. But I insist, this happens quite earlier on, like probably 10 meters in the subsurface. There is already quite a lot of particle alignment. And if we zoom in and we look at the organic matter that was made very, very soft and deformable, the organic matter also became quite aligned. Now, when we put these two together, the alignment of particles and the alignment of organic matter, two things come about. One is that clay control fabrics become very anisotropic very early on because of particle alignment during burial, but also they become fissile. That amazing characteristic of shales that you knock them and they split in planes, that is fissility. And that is the compounded effect of having clay particles alignment and organic matter stretching and alignment preferentially along these horizontal planes. So folks, we have come a long ways from the atomic scale all the way to the scale of shales. And we have summarized in today's presentation the interaction between all these. But in order to go back to understanding the details, I strongly encourage you to go back and see the previous two presentations on clays and clay-water interaction. There are a few references with few more details. Thank you.